Hey guys, welcome back to the lecture. So let's start with the revision of what we learned in the last lecture, okay? So in the last lecture we learned about what the bits are, right? Like when there are two sinusoidal waves of slightly different wavelength, slightly different frequencies, and when they overlap in the space, we hear sound, right? Something called frequency modulation. So the sound of like the soft, low, soft sound, okay? So basically, graphically it looks, two waves. They have a very close frequencies and they are overlapping. And we looked at mathematically, we can write the oscillation of a frequency, or the pitch that we hear, is given by this equation: frequency f oscillation equals half f1 plus f2. This is the average of the frequencies of those two waves, right? And then the bit frequency is given as the modulus of difference between the frequencies, modulus meaning the positive value, okay? So this sign here, right? This sign, okay? So that was about the bit frequency. And we also said, the application of bit frequencies, in the case like a radar detector that is used to determine whether your vehicle is speeding up or not, right? That's one of the example of many applications of a bit frequency. We also started with interference of wave from two sources, and then we came up with these two conditions, right? For constructive interference, we have delta L equal to m lambda, where delta L is the path length difference, right? So you have a, remember we use example of like two different speakers, and then you are standing somewhere at some distance, and then whether you'll hear loud sound or whether you will hear nothing, you won't hear anything. It depends upon whether the wave pattern forms constructive interference or destructive interference, right? So if we have, for the condition for the constructive interferences, the path length must be equal to the integer multiple of the wavelength lambda, where m equal to 0, 1, 2, 3, and so on. Destructive interference, the path length difference is m plus half lambda, meaning it has to be multiple of m plus half times the lambda, right? So this half lambda is the path difference that will enable us to get the destructive interference, okay? And we started the new chapter on wave optics, and then we said what is light a wave or a particle. If it's like a particle, and then if we have a slit here, a small opening here, when the particle goes in, it directly goes and hit there, and that is spot. That's like a boundary wall or a screen. Let's say we have a screen. If it's like a wave, then the water, let's say, example, water flows here, then what happens is behind this aperture, the wave is going to spread, right? So instead of just being at one point, it is going to spread. And then and we looked at a couple of scientists who favor or who proposed the theory of light as a wave model. Some other people, like Einstein, like Isaac Newton, he proposed this theory of light as a ray model, right, or a particle model. And then we said, based on there are basically three models of light propagation. In this chapter, right now we are learning wave model, and then in the next chapter we'll be learning about the ray model, a particle model, which has to do with the quantum. We have to talk, this falls in the area of modern physics, quantum mechanics. We won't do much about it. We would touch like a little bit of it, like at the end of the semester. Okay. And so we looked at a few properties of the light, right? So it travels, so wave model says light travels like a wave. It has a speed equal to c, equal to 3 times 10 to the power 8 meter per second. The speed of light in other material, it's not same as this value, which is a higher value, right? See, when the light travels in different materials, its speed gonna decrease. And then when it's in the other material, the speed is given by this equation, V equal to C by N, where N is a refractive index. Value of refractive index is greater than 1. And we also looked at what happens to how to get the wavelength in the wavelength of light in the material. Okay, so the wavelength in the material is given by this equation where lambda dash, we have lambda dash, which is equal to wavelength of a light in vacuum divided by the refractive index of a material. Okay, so right now N has to do with the medium where the light is propagating. Okay, so that medium has a certain value. It is greater than 1, and then which means, right, this lambda dash is going to be different than the lambda. Okay. Alright guys, so let's see. So we said if we have a light beam that is passing through a small opening, this is what we would get. This is called, so this is a small slit. Okay, actually let me grab and show this to you just a moment. Alright guys, the thing I wanted to get, I didn't find it. I thought I brought it from the university. I didn't find it, so don't worry. I'll explain it to you guys, okay? Alright, so if we have this is like a small slit. Example this. If we make a really tiny slit here, use a knife and make a really tiny slit here, and then we have we use the flashlight from here, and then we put some screen over here, then what do we get? That's the idea, okay? This slit here, this slit width is exaggerated here to show it to you, but it's really tiny. It's in like millimeter, like 0.1 millimeter or something like that, really small. Okay, so what happens is the pattern formed on the screen would be something like this. So this is called single slit diffraction pattern. You see there is a very high intensity in the middle, and then the intensity of the light is kind of goes away as we move away from this distance. That would be something like this. This point would be somewhere right here in the middle, and then the other point would be further away here, or above that center point or below that center point here. Okay, So light beam passing through a small opening, it's kind of looks like it spreads, right? Like, so it's kind of very similar to what happens with the water wave, right? Like look at in the sea, when the water wave they pass through these, in between these stones, a rock, they kind of spread, right? After they pass through the narrow opening. All right. Okay. So here we have scientist Thomas Young. He was born in 1773 and died in 1829. He gave this theory of Young's double slit experiment, basically Young's double slit interference in 1801. He was an English polymath, Quaker physician. He contributed to varieties of fields such as vision, light, energy, physiology, language, musical harmony, and other fields. His contribution is in the field of principle of interference and also in the field of wave theory of light. Okay, so we are going to look at the theory proposed by him for interference of light. So. Okay, so I have a diagram here. So here is a Young's double slit experiment. Here is a light source, this is the source, and then you see this is spreading, right? And there are just these arrows so that they spread that way, right? Not just that way, every way. So let's say we have two different aperture rather than single slit. Earlier we had a single slit. If we have a two slit, so what happens is both of these slit here, there is a slit, here is also a slit, they're at a distance d, and then we have a screen for measurement, to see the pattern, so it lies at a distance l, and then so what do we see here on the screen? Okay, so it's by name double slit, pair of slit, right? Two slit. Young's, it comes from his, scientist Young's, his name. Okay, this experiment comes from that. So here the thing is this: when the light goes here, each of these light, when the light is here, right? One source is here, but then light is here, but each of the hole now, right? Each of these slit are going to act like each of the light through each of these slit are now going to act like source, another source. Imagine this, if this is harder for you to visualize. Think about this. You are carrying one light bulb here, okay, like big light bulb here, you're sitting here, and then you you have something again like this. Let's make those two slit here, maybe we'll keep it like that. We have a tiny slit here, tiny slit here, another tiny slit here, I have a light here source. What happens is and then those slit, we have that hole, right? So when we look at here, what happens is for this hole, if we are to look at from here, you see each of these hole now slit are going to look like the light coming from, there is a source of light in each of those slit, right? So that's what this one is showing. And then this screen is way over here. In theory, this L, the length between the slit and the screen should be very, very larger than the width of this slit, okay? So that is the Young's double slit experiment. You may be wondering, well, we don't know what happens, right? So light source is here, one light source, but there are two slits, and then when the light enters here, each of those two slits, the light from each of those two slits are going to act like source of light, and then they are going to overlap somewhere as they go, right? It spreads out. Some of these waves, they are going to overlap, and then they are going to give rise to certain pattern on the screen that we can view here. And then it turns out that those patterns we see here are interference fringes. Okay, and we'll do more details of this mathematical in a few minutes, so you'll see. So how does it really look like in real life then? Some of you guys have already done the lab about this, so you guys are probably familiar. So it turns out it looks like this, right? If you have a single pattern, there is just the central maxima, really bright spot here at the center. If you have a double pattern, actually, see, there are patterns, they are of, they are bright, right? And then there are actually multiple bright fringes, not just one, right? Here we just have one big one. Here we have multiple bright fringes, okay? So you see, this is the double slit. This is the interference pattern produced by double slit, okay? Alright, so now let's dive into the interesting part of doing physics, more mathematical or quantitative analysis of this, okay? Young's double slit interference experiment. Alright, we'll do the condition for Young's double slit interference experiment in the next video, okay?